Everybody. This is Kurt again, and this is our second video on kinetics. Today we're going to be talking about two maybe more detailed things about the rates of reaction. So in our last video, we focused on just, how do we define it? How would we measure the rates of reaction? And now we're going to look a little more into the theory of it and how that relates the microscopic properties of a reaction to the macroscopic properties. And we'll start off by talking about this thing, collision theory. Again, we always have these big kind of academic sounding terms for these things, but collision theory is just really looking at, on a microscopic atomic scale, what is happening when a chemical reaction takes place and what factors there affect the rate of a reaction. So if we think about a reaction occurring, what's needed for a reaction to happen? If I have a reactant A and a reactant B, what has to happen in order for A and B to react to form something else? Well, so the first thing is I need a collision between the reacting particles, right? If A and B are far apart, they can't really react with one another. I need there to be sufficient energy in that collision, right? A and B are A and B. They aren't reacting and decomposing into something else because they're relatively stable. So if A and B collide, they have to have sufficient energy for there to be a change in the bonds there. And it has to happen in the proper orientation. Okay, so you might have a negative side to one molecule and there's a positive side to another molecule. But if the two negative sides of the molecules are colliding with one another, they're going to repel each other, and that's not going to produce a reaction. So they have to be oriented in the right way for there to be a reaction to occur as well. So then what is going to be the atomic scale factors that affect rate? If that's what we need for a reaction to happen, what's going to make a reaction go faster or slower? So we look at the frequency of collisions. In any given moment, how many collisions are happening? What fraction of those collisions have sufficient energy to react? And what fraction of those collisions have the proper orientation to react? Okay? So we can define the rate as just being all of these three things multiplied together. How many collisions per second? What fraction of those collisions have the right energy to react, and what fraction of those collisions have the proper orientation to react. Okay? So what would be the macroscopic variables then that would affect those things? Well, the temperature, right? If the temperature in Kelvin at least is proportional to the average kinetic energy, then if I have a higher temperature, there's going to be faster moving particles and there's going to be more frequent collisions. And the fraction of those collisions with sufficient energy is also going to be higher because now all of the particles are going to have more kinetic energy. The other thing that's going to affect the rate of a reaction is the concentration or the pressure. You can sometimes use the pressure to measure this as well, but higher concentrations mean you have more stuff in the same area, okay, or the same volume. And so it's crammed into a smaller space. Same deal with pressure. If you have a gas at a higher pressure, it means you have more stuff per unit volume. And so that's going to affect the frequency of collisions. How often are these particles interacting with one another and colliding with one another? Now you'll notice that of those three initial microscopic factors that affect rate, we didn't end up bringing up any macroscopic variables that affected the orientation piece. So the fraction of collisions that have proper orientation is not something that's altered. It's just kind of a limitation of every reaction, and some reactions can be really flexible on what orientation these particles collide with, and some are really restrictive. Okay, but it's not something that we can change by just changing the temperature or changing the concentration. So we can take that and now look at these things called rate laws. So a rate law is just an equation that relates the rate of a reaction to the concentration of the reactants. Okay? So if we go back to what we just said, right? We said the rate of a reaction is equal to the fraction of collisions with proper orientation, the fraction of collisions with sufficient energy, and the frequency of collisions. Okay, so if we looked at a generic rate law, it would look something like this. Okay, and that green rate, that's the rate of the reaction in molarity per second. The K is a constant that's specific for each reaction. And even the term constant, rate constant, is a bit misleading because it's not constant at different temperatures. So what's factored in there is kind of the fraction of collisions with proper orientation and the fraction of collisions with sufficient energy. But at different temperatures, those are, or at least the fraction of collisions with sufficient energy is going to be a different value, right? So the K is only constant. It's only the rate constant is only constant if you're at the same temperature. And the A concentration of A to the L, these are all the concentration of the reactants. Okay, we could use partial pressures if we were talking about a gas as well. And these L, M, and N, these exponents, those are called the orders of each of those reactants. Okay, so the exponents are called orders, and let's say we have a reaction. A plus 2B plus C goes to AB2C. Okay, some generic reaction. It's got this rate law. Okay, don't worry about how I got there, but let's say that that's the rate law. So rate is equal to the rate constant for this reaction times the concentration of A squared times the concentration of B. So we would say the reaction is second order in A because the exponent's 2, first order in B because the exponent is 1, and 0th order in C because C isn't even there. But if you imagined having C to the 0th power, that would just be 1, and it wouldn't affect rate at all. Okay? So we could also calculate something called the overall reaction order, which is just the sum of each of the individual reactant orders. So 2 plus 1 plus 0, we get 3. Note that the exponents do not match the overall reaction stoichiometry, right? So it was Ka squared, even though the coefficient of A here is 1, and it was B to the first power, even though the coefficient of B here is 2, okay? And we'll get to why that is later. So how do I figure out what the rate law is? Okay, and we're going to use this method called initial rates, where we look at how the initial rate of a reactant changes given some change in concentration. So we need to start off just by looking at some relationships. So looking at some algebra, some very simple algebra. So let's say we have this equation, y equals 5x to some power z, okay? And let's start off by assuming z is 1. So we have y equals 5 times x. So we need to look at, and this is what we're going to do when we try to figure out the rate law, we need to look at how a change to x affects the change to y. So if I now double x, and I go from x equals 1 to x equals 2. Well, when x was 1, right, 1 times 5 is 5, y was 5. Now when x is 2, 2 times 5 is 10. And so by doubling x, we've had the same change to y. Y has also doubled. If we tripled x, if x were 3, 3 times 5 is 15. So y is 15. So now we've tripled y. Okay? And this is what happens when the order of the reaction in this case is 1. So let's look at if z was 2. Oh, there's one more piece here. If x was 4, if it was 4 times the original value, we'd get 4 times the value for y. So if we look at now if z is 2, so now we have y equals 5 times x squared. So x is equal to 1, y is equal to 5. Now let's see what happens when x doubles. When x doubles, we get 2 squared times 5 is 20. So doubling x, we get 4 times the change in y. If we tripled x, 3 squared is 9 times 5 is 45. We get 9 times the amount, the change in y. The change in y is 9-fold. If we quadruple x, well, 4 squared is 16 times 5 is 80. So we get 16 times the change in y. And so you can see a pattern here now. If x is, or if z is 2, if the exponent is 2, I end up getting whatever change I have to x, I get that change squared in my value for y because x is squared. So if I do 2 times the x, I get 2 squared is 4 times the change to y. If I do 3 times x, I end up with 9 times 3 squared, right? And so that's going to work out for any value we choose. If we did 5 times x, 5 squared would be 25 times 5, and we would get 25 times the change in y. Okay? Again, just taking it to one step further, if we had a z of 3 and x were to the third power, we'd have y equals 5 times x cubed. Here x is 1, y is 5. When x is 2, y is 8 times as much. When x is 2, 2 cubed is 8. 8 times 5 is 40. We get 8 times the value of y originally. Okay, and that's because we're getting whatever the changes we're making to x, that change is going to be cubed and have a cubed effect on y, right? So if x were 3 times, 3 cubed is 27. 27 times 5 is 135. We get 27 times the change to y, right? So triple x, 3 cubed is 27. Quadruple x, and we get 64 times the change in y, because 4 cubed is 64. Okay? Again, this might seem like we're back in math class, but it's important to know how these relationships are related, because what we're going to do now is we're going to apply this to a set of data. So here we've got an experiment where we have N2O5 decomposing into NO2 and O2. It has these coefficients, right? There's the chemical reaction equation. And we do a few experiments, a few different experiments. In the first experiment, we have an initial concentration of N2O5, and we measure the initial rate, okay? And initially it's this. It's 2.1 times 10 to the negative third molarity per second. Okay, so that's one experiment. In a completely different experiment, experiment 2, we start off with 0.024 molarity of N2O5. And we have an initial rate of 4.2 times 10 to the negative third. Okay? And then we have a new experiment, experiment 3, with a new initial concentration of N2O5 and a new initial rate. So the question wants to know, or the question is asking, use this data, or wants you to do this, use this data to find the rate law, including the value and units of the rate constant. Okay, so the first thing we have to do is look at, again, what's given. So we have this reaction equation, and we have these this set of data. What's unknown is the rate law. So let's just start off by writing out what would be the generic rate law for this reaction. So we would say rate equals K, the rate constant, times the concentration of N2O5 to some order L. We don't know what the order of the reaction is with respect to N2O5 yet. And that's the first thing we're going to try and figure out, is what is this exponent here, okay? And again, relate this back to what we were just doing with that equation of y equals 5 times x to the z. So what we're going to do is we're going to change the concentration, okay? Here that's the x, and we're going to see what change there is, or what effect there is on the initial rate, that's the y, right? So if we look at experiment 1 and experiment 2, we've doubled the initial concentration, we've doubled the concentration here, and we've ended up with twice the rate. The rate has also doubled. Okay? So if we think back to what we were just doing, if I double x and I get double y, the exponent there, right, must have been 1. Because if z is 1, x, if I double x and I get double y, that would make sense based off of the math here. So if I'm doubling the concentration and I get double the rate, it's basically saying these things are directly proportional, and so the exponent here must be a 1. Okay? So here's our generic rate law, but now we've filled in what the value of L is, right? And normally if it's a value of 1, you don't even need to include that. So we could just write it as rate equals K N2O5 concentration. But now it wants to know what is the value in units of the rate constant. So if we isolate the rate constant, it's equal to rate over the concentration of N2O5. And we can actually now just go back and choose any of these 3 points, and they should all give us the same value. And I can just plug in the initial concentration and the initial rate there. So let's just choose point 1. So K equals the rate, 2.1 times 10 to the negative third, over the concentration, 0.012 molar. And we get the molarity cancels out, and the value we get is 0.175 with the units of 1 over seconds. Okay? So our final rate law is rate equals 0.175, 1 over seconds, times the concentration of N2O5. So now we have a rate law that relates the concentration of the reactant to the rate. So if I knew the concentration at any given moment, I could calculate what the rate is going to be. Great. Okay, let's do another example. Let's say we have 2A reacting with B to form A2B, okay? And we're given the same sorts of information here, but now we have 2 reactants, okay? 2 reactants. Again, it wants us to figure out the rate law with the value in units of the rate constant. So we have very similar information, but now we have initial concentrations of both of our reactants, as well as the initial rate. So our given, same information. Our unknown, same unknown. We're looking for the rate law. So here's our generic rate law. Rate equals the rate constant A to some power L, B to some power M. We don't know what L and M are. That's what we're going to figure out here. So from experiments 1 to 2, you'll see that the initial concentration of A doubles, but B stays constant. And the rate doubles. So if B stays constant, we can kind of ignore that, and I'm doubling A and ending up with double the rate. So that's kind of the same situation that we had before, okay? So if that's the case, then L is equal to 1, right? The exponent for A is equal to 1. So we want to figure out these situations where one of the reactants is remaining constant. In this case, it's B. The other reactant is changing, and how does that affect the rate? From experiment 3 to experiment 1, right? A is staying the same, 0.3 to 0.3, but now B is doubling. It's going from 0.25 to 0.5. And if we look at the rate, it's hard to see, but if I divided 3.46 times 10 to the negative 2 by 8.65 times 10 to the negative 3, we end up getting about 4 times the rate. Right, so the rate quadruples going from experiment 3 to experiment 1. So that's indicating that M has a value of 2. This exponent here is 2. Because if I double B and keep A constant, I get 4 times the rate. So it must be, in order for that to happen, the 2 that I'm multiplying B by has to be squared to give that quadrupling in the rate. So now we have a little bit more information filled in here. So we have rate equals Ka times B squared, but now we want to figure out K again. But again, we can just solve for K and plug in any of these 3 points. So in this case, we'll take the third one in this case. So 8.65 times 10 to the negative third molarity per second over 0.3 molar, right, was the value for A, over 0.25 molar squared for B, because B was squared here. So now the actual value I end up with is 4.61 times 10 to the negative third. And notice the units here are 1 over molarity squared times seconds. So that's different from the units we got before. And that's because we have a different reaction order, right? Here we have the rate constant is always going to be equal to rate over, the reactants raised to their reactant orders. And so depending on what those orders are, we're going to end up with more or fewer molarities in the denominator, and that'll affect the value of K. Okay? So if I know this information now, again, I can figure out the reactant orders and the overall reaction order just by looking at what are these values. So it's first order with respect to A, second order with respect to B, and third order overall just by adding those two together. So just to recap, so now we've got collision theory, which focuses on what's happening on the microscopic level, and then how does that relate to the macroscopic variables, and how do those relate to the rate, right? So a rate law is an equation that relates the rate of a reaction to the concentration of its reactants. It includes that temperature piece as well, but in the rate constant. Rate laws can only be determined through experiment, right? So that's how we figure this out. We look at this rate data, we do these kinetics experiments, and then we figure out what is the rate law from that information. Rate constants incorporate the energy and the orientation part of collision theory. They have variable units, right? So depending on the reaction order, you'll get different units for the rate constant, and the temperature will always affect the rate constant. So the rate constant is only constant at a given temperature. Higher temperature, you'll have a higher rate constant. And then we also figured out how to calculate the rate laws and the rate constants with units from initial rate data. And then we determined the reactant order and the overall reaction order from that rate law. Okay? So that's it for this video. There's a lot there, but I think if you can get a start on some of the homework problems that we'll be doing and we'll be continuing in class, I think it'll give you an idea of where this all comes from. Come to class with some good questions, and yeah, we'll see you tomorrow. All right, bye.